Hi, this is Brandon Baines in the Math Department at Lipscomb University, here to talk with you about solving logarithmic and exponential equations. In this presentation, you'll learn how to solve logarithmic equations, and you'll learn how to solve exponential equations. Both of these will make use of the definition of logarithm. So, in App 5, we learned the definition of logarithm, and we learned that it provides us with a way of going back and forth from logs to exponentials, as well as from exponentials to logs. We're going to use our ability to do that is the ability to go back and forth between those two representations to solve problems involving population growth, compound interest, as well as other applications involving logs and exponentials. It may be helpful to go back and review that definition of logarithm from App 5 before proceeding in this presentation. Here's an example. A young man invests $5,000 into a savings account bearing 2.5% interest compounded continuously. This is a familiar scenario from App 5. This is a continuously compounded interest scenario. The question we're going to ask here is going to be slightly different than what we asked in App 5. So the question we're asking here is how many years until the account has doubled? So notice that is different because in App 5, we would say in, for example, 20 years, how much money is in the account. When we substitute the values into our continuously compounded interest formula, the result here is 10,000 equals 5,000 e to the 0.025t. The amount is 10,000 because that's double 5,000. We want $5,000 to double, would be $10,000. To solve for t, to solve for the amount of time it will take for this amount to be $10,000, we're going to rewrite this equation as a logarithm. Before we can do that, we need this to look just like the definition of logarithm from App 5. And when you go back and look at that, you'll notice that the exponential equation has 1 as its coefficient, not 5,000. And so before we can proceed with that definition, we need to make sure that the coefficient here is 1. To do that, we'll divide by 5,000 on both sides. That results in this equation here. 2 is equal to e to the 0.025t. Rewriting as a logarithm results in the equation natural log of 2 is equal to 0.025t. Divided by 0.025 on both sides, we have the natural log of 2 divided by 0.025 is equal to t. Using a calculator and rounding to the nearest year, we see that t is approximately 28 years. So it is in about 28 years, the account will have doubled. Let's consider another scenario. Researchers are studying a new strain of a certain bacteria by observing the growth of the bacteria in a petri dish. They begin with 100 bacteria in the petri dish and measure the amount of bacteria each day. The researchers model the growth of the bacteria with the function a equals 100 e to the 0.3t, where a represents the amount of bacteria t days after the bacteria is placed in the petri dish. This is also a familiar scenario from App 5. In App 5, we ask questions like, In App 5, we ask questions like, in 30 days, what's the amount of bacteria in the petri dish? In this app, we're going to ask questions like the following. When will there be 1,000 bacteria in the petri dish? This requires us to be able to solve for time in the equation. 1,000 equals 100 e to the 0.3t. Again, our method of attack for these kinds of equations are the method of attack is to rewrite as a logarithm. Before we can rewrite as a logarithm, we need to make sure that this coefficient here is 1 so that it looks just like the definition that was stated in App 5. So we divide by 100 on both sides, results in the equation 10 is equal to e to the 0.3t. Rewriting this as a logarithm using the definition of logarithm, we have natural log of 10 is equal to 0.3t. Divided by 0.3 on both sides results in natural log of 10 divided by 0.3 is equal to t. Simplifying using a calculator and rounding to the nearest day, we see that t is approximately 8 days. So in approximately 8 days, there will be 1,000 bacteria in the Petri dish. Let's consider a final example. The function f of x equals negative 4.4 log of x plus 28.5 models a percentage of women voting Republican X years after 1969. In what year will there be 25% of women voting Republican? Since f of x represents the percentage of women, we're interested in knowing when it will be 25%. We have the following equation. 25 is equal to negative 4.4 log of x plus 28.5. To solve this kind of an equation, we will still use the definition of logarithm. And in this case, since it is logarithmic already, we will convert to an exponential equation. Before we can do that, we have to make this equation look like the definition of logarithm as stated in App 5. So that's going to require us to have the logarithmic expression isolated. That's going to require us to subtract 28.5 on both sides of the equation. That's going to result in negative 3.5 equals negative 4.4 log of x. It's also going to require us to divide by negative 4.4 on both sides of the equation. That results in the statement the log of x is equal to negative 3.5 divided by negative 4.4. Now, this looks like the definition of logarithm as stated in App 5, and we can rewrite this as an exponential equation. Using that definition, we get that x is equal to 10 raised to the 3.5 divided by 4.4. Using your calculator, you get that x is approximately 6.24 years, or rounded to the nearest year would be 6 years. Since x represents the number of years after 1969, we would know that during 1975, 25% of the women were voting Republican.